it makes sense for us to get started. This next session is on machine learning, and it features some of our illustrious alumni that have been working in this area. We're really excited to welcome all of them back. Our first speaker is Sid Banerjee. Sid finished his PhD here, working with Sanjay Chakratai and Sujay, right? And Sujay Sangavi. He then did his postdoc at Stanford, working with Metro Ari, and now he's assistant professor at Cornell. Sid, great to see you.
Thank you. Thank you all for showing up after lunch. I noticed both my advisors haven't made it yet. So it is really amazing that all of you did. I'm like doubly grateful. So it is. So before I start, a big thank you to all the organizers for inviting us back. It's been amazing meeting up with a lot of people. We were here with somewhat strange seeing the new building. While we were, this is the first time I'm coming here. I used to joke that I would go out of the old building and it would sort of go down right behind us. They would blow it up when we finished our defense. They never did that, but they destroyed it soon after we left. And this is an amazing space to do work. Really glad to be back. So, as Constantine said, I'm right now in the School of Operations Research at Cornell. This is joint work, so there is some work which I first started off at Stanford, sort of continued doing it afterwards with an undergraduate student at Cornell, Nitin Shankumar, whose name by mistake appears at both places. And then I'll talk about something which is a little more recent, which I've been doing with a graduate student of mine, Alberto Vera. And sort of to start off, is this thing on? That's not. So what is this talk about? So this whole session is about machine learning, and we'll hear a bunch of talks about why machine learning is really cool and how it's going to change the way we do everything. And in some senses, it already has. And there are a lot of really amazing uses of large-scale data in practice, which we've gotten so habituated to, we've kind of stopped appreciating the magic behind what's going on. I'm going to talk about sort of two problems or two such applications of machine learning, which I think all of you would have experienced at various times. So the first one is social network recommendation. This was me going a little while back and looking at my Twitter feed. If you look at the side of your Twitter feed, there's a thing called who to follow. And this is Twitter suggesting a bunch of people I should follow who I don't follow. So one sort of high-level comment about this is this, it's quite a remarkable list. In some sense, just going through this, you get a very good sense of what I do and who I am, what I work on. So I work on problems at the intersection of computer science and economics. So very clearly see that reflected in the suggestions. I am an Indian, and Twitter is kind of myth that I don't follow the Indian heroes such as Tendulkar. I do listen to a lot of NPR, This American Life. You can sort of just look at this and get a very good picture of who I am as a person. And what most of us don't think too much about is how is something like this computed. And I have the pleasure of actually doing my postdoc with the person who made this tool. And the way this is done is using something called personalized PageRank, which is a variant of the famous PageRank algorithm, which in some sense all of us have been touched by the last 10 years or so. Another application, a little more recent than PageRank, with one which, again, I think most of us have gotten used to by now, is just doing network routing. So me in the morning, I was staying in West 6th Street, where I used to live, and I wanted to come to the EERC, ask Google to tell me how to do that, and Google gives me these routes. And kind of going back to the Clay-Sharp report, these applications, this sort of notion of social network recommendation and just route recommendation on networks, they've become so ubiquitous that we've kind of forgotten what was magical about the fact that this could be done in the first place. So what is remarkable? In some sense, if you just look at the routing example, most of us, if we ever do a course on algorithms, the first thing we are taught is something called Dijkstra's algorithm, which computes shortest paths. As an aside, Dijkstra was once upon a time in UT. And it feels like all Google is doing is that they are implementing Dijkstra's algorithm. There's nothing fancy about that. They have a network, they're just looking at it, they're implementing Dijkstra. If you think a little about it, there's no way this is feasible. So firstly, this network is huge. How did Google know beforehand that I was going to stay in this arbitrary location in West 6th Street and want to go to this location? I mean, there's no way Google API knew what I was going to ask for. And I'm not the only person asking. There must be millions of people at any time. I would conjecture on the order of minutes, there must be like at least thousands, if not millions of people trying to do this query repeatedly. If you try doing Dijkstra on something like this would never work. There is no way this would scale to become as ubiquitous as this. And it's the same thing with social network recommendations. PageRank was easy because PageRank was one list for everyone in the world. So in some sense, we took all the web pages in the world and we said, this is how important each one is. Here, Twitter is actually finding who is important for me personally and doing it separately for everyone else. So kind of the magic of personalization is not that we are solving these optimization problems, we know how to do this. It is that we are solving it for everyone who wants this problem to be solved, and we are solving it at incredible scales and incredible speeds. And that's what this talk is about. So it's, in some sense, the magic in network, in the way we use network data today is not that we can do amazing things with network data. This we knew for a long time. We knew we had amazing data, we knew that there was amazing information in them. What's remarkable is that we are able to take these problems and solve it for everyone simultaneously. And what I'm going to sort of talk about is that even though this is true, there are only very few canonical problems for which we've been able to do that. And going slightly beyond these canonical problems has already got really difficult. But these problems are getting increasingly important, and there's a huge number of people sort of looking at these problems of how do we solve these optimizations of the same network, where we have the same network for everyone, but different people asking different questions. How do we take advantage of this and solve it faster? Why is this important? Here are sort of two examples. This is Twitter again. But instead of searching for whom I should follow, what I've done now is I've searched for Adam, or this was actually my co-authors just searching for the name Adam. And now what I would expect Twitter to do is tell me which people in the world whose name is Adam I should follow. Except they're doing a really bad job of it. So if you look at the list of queries, so the first one is Adam Lambert. When we did this search, we had no idea who Adam Lambert was, which tells you a lot about us, but we later went and found out who Adam Lambert was. You may sort of say, okay, that's your fault, you didn't know who Adam Lambert was. I would sort of question the second result now. The second result here is someone called Tommy Joe Ratcliffe. There's nothing about Adam in his name. It just turns out he's the guitarist for Adam Lambert. And somehow Twitter thinks that when I search for Adam, that's the most important thing to show. So something broke down as soon as I went from just trying to figure out whom I should follow to trying to figure out which people whose name is Adam I should follow. And what's really going on is that finding one list of names is easy. You just find a bunch of names and store them to the top 250. If I change the query, if I tell Twitter, no, I'm only interested in people called Adam, then all of a sudden Twitter doesn't know what to do. And the reason is just computing this sort of personalized centrality metric. We know how to do it, but doing this at query time is just impossible. It was impossible to do. So this is on the left-hand side, I'm showing the same search. We've taken the same sort of results, resorted it by the algorithm that we have. We can do it fast enough, and you can see that at this point, the top names turn out to be the CEO of Twitter, the CEO of Quora, etc. So people who are somewhat more important for what I do, somewhat more relevant. There's the same point when we are thinking about routing applications. So Google is pretty good at sort of telling you one path or a couple of paths from one place to another. They're not particularly good at handling traffic. So they do a decent job of it. They're getting better as we go along, but there are sort of applications coming up where we need to be really, really robust about this routing application. So I do a lot of work with a company called Lyft, and one of the products that we were looking at is trying to make a shuttle service. So this is in the Bay Area where if you want to go from one place to another, Lyft basically sort of combines, like it shares you up with someone, or it finds someone else taking the same route and kind of pairs you up with them. But for an application like this, the person driving is actually just like maybe commuting to work and they're doing you a favor by giving you a lift. They're really particular about the timing. So if Lyft tells me that you will go and pick this up in 6 minutes, both of us, both me and the driver, need to realize that 6 minutes is tight. We have to be available at that time. There can't be any mistakes in this. And similarly, it has to sort of figure out like the ETA, the drop-off times exactly. So in an application like this, finding the shortest path is actually not as important. What is more important is you should find a path where we can give a guarantee on the time with very, very high probability. So maybe there's a path which is shorter, but maybe once in a while there's like a long red light which sort of throws things off, or maybe once in a while you have to take a free left turn, and that takes a lot of time, and that would sort of completely throw off these predictions. So what we really want to do is we have a lot of data about the traffic. We have past data, we have current traffic data, we have distributions of what the time is on each of these edges. What we want to do is we want to get reliable travel time estimates. So we want to get a distribution of the travel time and say, okay, with 99% probability, if you take this path, it's not the shortest, but it will get you there in 20 minutes. And it turns out just this small change of moving from shortest path to doing a constrained shortest path, so solving shortest path with one constraint, actually makes it much harder. So shortest path can be solved for a long time, constrained shortest path with even one constraint is every. And so what we do right now is we take most companies, they take the traffic data and they just give you the averages, so they give you the shortest average traffic time, but they're not using the statistics in any way. And that's kind of the question we wanted to answer. So, I mean, this is just two examples which I've been working on. But what me and many other people have really been pushing is going beyond the canonical examples where we know how to make things faster and trying to get these sort of network personalization, this scalable network personalization applicable for many other things. And this is sort of a short summary of what I'll try to talk about in this talk. Essentially, the way any of this network personalization is done is you use some amount of preprocessing. You know that the network is not changing over time, so you can do something with the network beforehand and calculate some sort of a sketch of the network, which makes it easier to solve these problems. But as soon as you do that, there's a sort of trade-off between the preprocessing and the storage and the query time. So in the case of, like, let's say the PageRank problem, there's an easy way to get fast query times. I just calculate personalized PageRank for everyone and just store it. So do a table lookup. That's huge amounts of storage. So we somehow want to explore the space of what are the trade-offs between the processing time and the storage and the query time. Okay. What we want to understand is like what properties of the network can make this easier or harder. And this is like essentially we want to give performance which is not in the worst case, but somehow depends on the network that we look at. And what I've been really excited about and what part of this talk is about is using bidirectional methods. So all the problems that I told you, I actually know a source and a destination, but typical algorithms of doing it would sort of ignore one and just calculate it for every destination. So what speedups can you get if you use a bidirectional? Again, the short story. So just here's a brief intuition as to why these methods are even useful. A lot of us have started looking at this, but essentially, in order to understand why a bidirectional method helps, you can go back to the simplest problem of I give you a network, I give you two nodes SMT, and I want to find the distance between them. And in some sense, if you knew the network is D regular, so if every node has degree D, the simplest way to do it is you just start growing a ball from S until you hit this node D. And if the length of doing this was L, you would need time which is D raised to L. Every time every node has D neighbors, you sort of keep getting D in the first round, D squared, D cubed, etc. until you hit this node D. Now, in the same problem, if you sort of, instead of doing this, you can grow the balls simultaneously from both S and T. So you can grow two balls around these nodes. And now what you're trying to look for is when do these balls intersect. That's not trivial to do, but we sort of have data structures now which can do that efficiently. But assuming we can do that fast, you can immediately say that the running time goes to square root of D to D. So it goes to D raised to L over T. That's how long it takes for the balls to intersect. And we're getting a sort of square root speed up from one to the other. And at a high level, what we've been able to do over the last few years is sort of extend these ideas of bidirectional search to both PageRank and constrained shortest paths. kind of proof by picture. In PageRank, what we can do is, there was two well-known algorithms which were the state-of-the-art for computing personalized PageRank. That's in yellow and green. The blue plot is what times we get on various networks. The important thing to note is that the y-axis is in log scale. So we're getting orders of magnitude improvement compared to everything else using these bidirectional techniques. And so a similar story for constrained shortest paths. So this is more recent work, so I don't have fancy plots, but what we're doing here is we are trying to compute constrained shortest paths, and this was the San Francisco traffic network. The important thing to look at are the last two columns. So that's the query time using Dijkstra's algorithm in milliseconds, and the query time we get using our bidirectional technique called hub labels in milliseconds. And again, you can see sort of orders of magnitude, so 10 to the 4 orders of magnitude. Now, of course, I'm cheating a bit in that Dijkstra is not using any storage, but this is the storage I'm using. So for every node, I'm sort of storing something like 36 extra nodes. And this is a network with like, I think 2,500 nodes. It's not a huge amount of storage to get these nodes. So the brief we got was to kind of give you a sense of what we're working on, and also give you a brief sense of what the techniques are. I have 1 minute to go through the techniques, and I think in the interest of time, I'm going to do a sort of an impressionistic pass through of all the math in this. Essentially, I mean, the high-level idea is that I told you it's impressionistic. So there were sort of two known algorithms for computing PageRank. So you could either do Monte Carlo forward, or you could do what's called a variational method. You could do local updates backward. And what we were able to do is we came up with a way of essentially combining these two. So instead of doing a local update, so instead of doing the local power iteration backwards all the way, you do it half of the way, figure out when you should stop doing it, and then resample it using Monte Carlo. And this works. You need to be a little more careful about how you do this definition, but what you can prove at the end of this is that you can compute the personalized PageRank for any network in time which is square root of the number of pages. This is actually kind of remarkable. There's a magic trick going on underneath, because I'm estimating a probability of order p in time square root p. This should model in time 1 over square root p. So there's some model reasons why this should not be possible, but you can, by storing the right data structure, we can get around this. And we've sort of been able to use something similar for constrained shortest paths. This is a much harder problem because we have to do the exact shortest path. We can never approximate if I'm giving you travel directions. But it turns out that there was a known scheme based on what I call hub labels. Now giving guarantees is much harder, but there was amazing work 5 years back by the folks at MSR where they figured out a way of giving guarantees based on something they call the highway dimension, and we were able to extend that to this problem. Essentially, the summary in words is that in all the problems where shortest paths are easy to find, so in all the mapping applications that we use right now, finding constrained shortest paths is essentially as easy as long as there's this technical condition which we call the partial. Now, I'm done. Okay. So the last thing I wanted to sort of leave you with is this quote over here. So I actually don't work only on machine learning. The thing I'm much more interested in, and the thing which I think is getting more and more interesting as we go forward, is machine learning in some sense is getting commercialized. We will all be able to do machine learning, or most companies will be able to sort of have access to really advanced AI and ML. But a somewhat more interesting thing, at least something which is much more interesting for me, is that there are these sort of interesting structures of marketplaces which are emerging between these companies, and companies are somehow putting off doing these complex computations and using a market to do that. Preston McAfee is the chief economist at Microsoft. Before that, he was actually at UT for a long time. So the quote about Uber, and it's something which is very close to me because I work on these problems, and kind of moving ahead, I expect when I come back for the next 20th anniversary, I'm hoping to talk about, like I'm hoping this is the next big thing, and I'll talk about some of these results. This is a great building, but I must leave you with another great building. That's the office at which Yudong and I work. Thank you all very much.
One question on
constrained time approach, and so the data becomes raw. How quick does it take to reshuffle if everyone's using the same approach?
It's a great question. So that's why I'm sort of suggesting that there are limits to these data mining approaches. That is exactly one of the limits. If everyone starts believing in it, it kind of starts corrupting it. We know there are ways of getting around it. There's a talk by Aditya later on Bandit problems, but I genuinely feel the more appropriate answer is that this is going to move to a regime where there's a marketplace controlling who gets access to your data, and that's a problem we need to understand.
Thanks a lot, Sid. Our next speaker is Yudong Chen. Yudong was the great fortune of having the greatest advisor ever. He then went to do his postdoc at Berkeley with Martin Wainwright, and at the same time as Sid, he joined Cornell in the ORIE department, and he's been there. This is his third year. It's really great to have Yudong back. Take it away.
Thanks a lot for inviting me back. I haven't been back since I graduated, so this is my first time back in UT for 4 years. And so actually I'm going to talk about something that is different from what's on the schedule. Talking about. So I'm told I shouldn't talk about something too technical, and on the schedule you see something that is already a sensor version of a more technical thing. But I think this will be more interesting for the audience. So this is a work that I started when I was at Berkeley, and then later I worked with the world's greatest advisor, Constantine, and two of his students. So I'm going to talk about how to take advantage of non-complex optimization for faster machine learning. So I generally work on this area called high-dimensional statistics or high-dimensional machine learning, where the goal is to, we're given a very large data set, high-dimensional, there is a lot of features, a lot of data points, and we want to identify some intrinsic low-dimensional structures in this data set. And these are just some of the examples that we have looked at. We want to find sparse solutions to regressions with many variables. We want to find low-res solutions to a problem which otherwise involves very large matrices. We want to identify clustering structures that are hidden in a lot of nodes. And we want to identify Markov structures, outlier structures, etc. And in this talk, I'm focused on one of such problems, robust PCA. And so the problem is simple enough. We are given a we have a low-rank matrix L star, and we have a sparse matrix S star. You think of this low-rank matrix as your signal matrix, and your sparse matrix as some sparse fraction. And what we observe is the sum of these two matrices Y. This is my data, and our goal is to decompose this structure. So given Y, I want to recover this low-rank matrix and the sparse matrix S star. And this problem has, of course, many applications, from recommendation systems to networks to graphical models. But we are actually motivated by this very interesting application in foreground-background separation. So let me show you some videos. So this is the problem we are looking at. We have a video that looks like this. There are people moving around in the foreground, and there is this background of this coffee shop that is not changing. And our goal is to separate these moving objects from this static background. And this turns out can It's a special case of the robust E-state problem. You think of this static background as the low-rank matrix, the low-rank part, and this moving objects as the sparse part, and you want to separate them from each other. And of course, we want algorithms that are good in two metrics. We want the algorithms to be fast, that are able to handle large data sets, and we want the algorithm to be statistically accurate. We want them on the algorithm to accurately separate this foreground and background. And so this is the goal. And for this problem, in the past 10 years, a lot of the algorithms are based on convex relaxation or convex optimization. So remember that the original problem involved some non-convex structures. The low-rank structure is a non-convex structure. Sparsity is a discrete combinatorial notion, which is also non-convex. And people used to think that non-convex optimization is hard, and to get an algorithm that is easier to solve, they look at the convex relaxation of it, where we replace the rank using this convex relaxation called the nuclear norm. So this is the nuclear norm of L, and then we replace the sparsity by a convex function, which is the L1 norm of S, which is just the sum of the absolute values of the entries. And since our goal is to separate our data Y into a low-rank part and a S part, and so instead of using the rank and sparsity function, which are non-convex, we just try to minimize their convex properties, which is the nuclear norm and the L1. So this is a convex relaxation of the original non-convex problem, and it turns out in the last 10 years, this convex relaxation approach has been shown to be very successful. Because it's a convex optimization problem, it can be solved in polynomial time, and you also have very strong statistical guarantees that this algorithm can recover the low-rank matrix L star even you have a very large fraction of sparse interruptions. And in terms of time complexity, this problem is complex and actually can be formulated as a semi-definite program, and you can use all of those algorithms developed for SVP to solve this problem. If you use the off-the-shelf solver, it takes n to the power 4 times, and if you use a more specialized solver, it takes n squared time, where n is the dimension of your matrix. So it's, in some sense, it seems like this problem is solved. We have an algorithm that can be solved in polynomial time, and it's very robust and accurate statistically, but we're never satisfied. We still think that this kind of n squared time complexity is still too high. Think about a matrix with 1 billion rows and 1 billion columns. So this will solving such a problem will take time 1 billion squared, which is still too slow. So in this talk, I'll give you a linear time algorithm that takes time linear in n instead of quadratic. And the key idea is that we will not do this complex relaxation business. We will look at the original convex optimization problem, which people used to think is hard, but I'll try to convince you that it's actually not as scary as you might think. We can actually develop algorithms based on convex optimization that are both fast and you can get rigorous, provable performance guarantee. So this slide summarizes our algorithm. So the first step of our algorithm is to sparsify the data. Our original problem involved an n by n matrix. I will not use all the data in this matrix. I'll just sample roughly a linear in n number of entries from this large matrix. So I'll subsample. I'll sparsify this matrix. And then, given this specified data, I'll look at this original non-convex formation. So recall that our goal is to separate this Y matrix, the data matrix, into a low-rank part and a sparse part. And one way to enforce the low-rank structure is to write my matrix as this factorization form, U-V transpose, where U and V are both skinny matrix with n rows and r columns. So this forces the matrix U-V transpose to have rank at most R. Oh, really? Yeah. So this is the original non-convex formulation. And how to solve it? You just apply the first algorithm you can think of. You just do this local update. You update S by some kind of local sorting. You update this variables U and V by gradient descent. And the hard part is that this is a non-convex problem, so the classical theory for optimization only guarantees that gradient descent converges to a local minimum, and we don't know how good the local minimum is. But we'll show that actually we can actually prove something for this non-convex approach. And computationally, we can show that the gradient descent actually converges geometrically, not just to a local minimum, but to a global minimum of this problem. And the overall running time will scale linear in n rather than quadratic. And at the same time, we show that this is not just a heuristic algorithm. We can prove rigorous performance guarantee that are similar to the previous convex optimization approach. We can still tolerate a large amount of sparse corruption. And instead of going through the proof, let me give you this example. So recall that this is the original video. And we run our algorithm. This is the background that we extracted. It seems that our algorithm is doing a pretty good job. And this is the foreground, which also seems to be accurate. And we also compare our algorithm to some of these other algorithms that people have previously proposed. For example, this one is based on the convex optimization approach. And you can see that it's actually not doing as a good job as what we do. You can see there are still these shadows in the background. So our algorithm, which is based on convex optimization, seems to be pretty accurate. And in terms of running time, this previous algorithm takes, for example, convex optimization takes about 7 minutes. Our algorithm used 80 seconds.
She's more than the time you have left.
So, to sum up, we have the algorithm, which is based on convex optimization. It's faster than convex optimization. Is more accurate than the convex optimization. And I think the take-home message for you is that non-convexity is not as scary as you might have thought. We can actually prove something and get something fast using non-convex optimization. And I use robust TCA as just one example, but actually we have looked at many other problems that we can actually take advantage of non-convex optimization to develop faster algorithms with provable guarantees and strong performance. So that's it.
Great. Let's thank you, Don. So let's take one question while our next speaker is setting up. So, any questions for Yudong? Okay.
I just, as far as you applying the algorithm to different things, have you ever applied the audios to the
Wait. Repeat the question.
So I'm thinking about how you try to find the algorithm for music, so the song, so it's just the way the instrumental is just the way the focus.
So the question is that have we tried to apply our algorithms to audios to separate the instrumentals from the voice? That's a very interesting problem we haven't tried, but I think it might have similar structures and properties as the EQ. And I think non-quantity might be also useful.
Okay, very good.
All right, so let's thank Yudong again. Next speaker is Aditya Gopalan, who received his PhD with Constantine and Sanjay, and he postdoced at Technion with
Chen and he's currently a professor at the Indian Institute of Science. So, take it away.
Thank you. I'd really like to thank all the organizers for inviting me here. I'm coming here for the first time in the last 6 years. So I graduated in 2011. So I'm simultaneously happy and sad. I'm happy because this is a great new building. Very glad for the students. What makes me sad is that I no longer see JP's Java on campus. And I surely think students' productivity will be affected by that. I did most of my PhD from there. So I'm going to give you a very brief tour of a class of, you can say, machine learning problems. In fact, it represents one of the simplest classes of what are called reinforcement learning problems. I'm going to go in the reverse order and try and talk technical first and then illustrate to you why these problems are important. Okay, so just bear with me for a minute. So this is joint work with my collaborators Shai Manor and Ishai Mathur in Israel, and Shai Chaudhary, who is a student of mine at IIS. So the problem I'm going to talk about essentially for this whole talk is what is called the multi-arm bandit. Okay, so essentially it's a problem about a bunch of actions or decisions that you have to make. So think of each as just a coin that you have to toss, and you don't know the bias of the coin. Okay. So each of these choices could be either very simple or very complicated. We'll come to the complicated part later. But think of these as, let's say, if you're a wireless system, you have a bunch of transmission frequencies to select. You have a bunch of, let's say, scheduling decisions to make. You might basically, each of these might be an ad to show if you're a recommendation system design, okay, like what Siddhartha talked about on the Twitter page. Okay? So just a bunch of choices, very general, nothing more here. Think of these essentially for simplicity as unknown biases of points. Okay? So the game that you play is as follows: at each round of 9, you are allowed to basically toss one coin. So let's say you toss coin 2 and you basically collect a reward based on the outcome of that coin. Okay, so that coin returns 1 or 0 depending on whatever its bias was. Let's say for simplicity you collect $1 if it came up heads and 0 if it came up tails. Okay. So you can decide to choose basically one coin to toss in each line slot and you play this game for a while. And your objective is to try and maximize the total reward that you get. Okay, so maximize the total dollars that you get. Okay. Of course, you don't know all these biases a priori. If you knew them, the simple thing would be to just toss the coin with the highest bias, so that it gives you the longest average, okay, largest average. But of course, you're having to learn this over time. And this is a fairly general, simple, abstract model to model decision making in an online fashion in many systems. Okay. Just by way of example, sort of the modern sort of application where this kind of basic primitive is used is recommendation systems. When you go to your Amazon or to your Twitter page, you get recommended a bunch of items. So the system is trying to recommend items to you and it's treating those as decisions. And you are the unknown for the system to learn. Okay? Of course, this is a very wide primitive in many applications. I guess the wireless or communication specific applications are highlighted in red. We have cognitive radio, we have dynamic frequency selection, rapid resource allocation. You can also take this to the extreme when you have really large number of actions between which you can choose. Each of these can actually be a parameter setting for a very complicated system. Okay? So imagine you're trying to optimize parameters that you want to set in some really large system. Each of these choices might represent an entire value, multi-dimensional value for a parameter that you want to set. We'll come to that in a minute. Okay? So there are a bunch of strategies or algorithms that can help you sort of deal with this uncertainty and try to solve this problem in a nice way for you as quickly as possible. But one of the sort of very interesting algorithms that has been around for a really long time, in fact it's prehistoric, dates back to the 30s, is what is called as function sampling. Okay? And it's a very nice and simple and fairly cool idea. All that you have to know is what is called Bayes rule in probability. Okay? So what it assumes is the following. Suppose I have to play this game with 2 coins. Of course, I don't know the biases of these coins. I just put, let's say, a uniform belief on my on the distribution of the bias for each coin. So I assume that, let's say, there's a uniform belief that I have that each coin's bias can be between 0 and 1. It has to be between 0 and 1. In order to play or toss a coin, what I do is the following. I just draw a random sample from my belief. Okay, so coin 1 returns some point in the blue coin there, and the draw from coin 2's belief returns some point there. And I just play the higher of these two. Okay, so in this case, in the first time set, I would have played on 1 because its sampled bias, according to my hallucination, is larger than the one for coin 2. And once I do this, I play the arm. I get to observe the actual reward, the dollar reward, which is 1 or 0. And using this feedback, I can update my belief about what the bias of coin was. Okay, this is by something very simple called Bayes rule. Okay, this is what is called as a prior to posterior update, okay, in statistics. So now you are faced with an updated belief about the biases, 2 biases of these coins. And in order to, you just repeat the same prescription over and over again. Okay, so you just sample one more bunch of samples from there. And eventually, as time progresses, the hope is that you will sort of explore enough against these, across these 2 alternatives, and eventually you will be doing the right thing. Okay, so it's a very, very simple prescription, and I show that it's surprisingly general as we move on. Okay, so essentially, the prescription is just sample from your belief, act greedily, and repeat. So in practice, of course, it's existed for a really long time. Been applied to various applications. It's been seen to work very well. In theory, we now know that it works very well, very, very recently, and this is rather surprising. And this has sort of sparked off a lot of interest in sort of revisiting these kinds of old schemes for doing much more complicated online learning problems. Okay? So more generally, so the standard, sort of the toy multi-arm paradigm is rather simplistic. Okay? The reason for that is because, so imagine that each of these arms is a frequency that you want to select in a wireless system. Obviously, there are relationships between the utilities or the returns of these arms. Okay? So if sort of 2 frequencies are similar, you expect their average utilities to be similar and so on. So there's no structure that's being modeled yet. You want to try and bring in the concept of sort of structure or correlation. So that even though you have a really large number of alternatives, you can learn across them by sort of utilizing feedback more cleverly from whatever you play. Okay? So here is sort of one attempt to generalize this drastically beyond the standard model. So imagine that these n things are not really your decisions, but they are some sort of parameter that represents your own system. And what you have at your disposal as actions are a bunch of sort of different types of actions, which we call complex actions. I'll give an example of this in the next slide itself. So what you play could essentially give you sort of very noisy feedback about the actual state of the system represented by the n parameters per top. So these complex actions could be subsets that you choose, or it could be parameter settings that you force on the system. It could be certain rankings of items that you display on a web page and so on. So each of them represents a decision. And imagine that you can specify what happens when you basically play a complex action according to a given system parameter. Okay, so you may say that I can basically choose 5 of these ads to show to a user on a given page, and when I show these 5 ads, the utility of this selection is modeled by, let's say, the sum of all these rewards. Okay, so the moment you have a specification like that, so this is an example of such a problem, for instance. It's sort of similar to what Siddhartha also talked about. It's an online routing problem. So the problem is as follows. You have a network and you have to route packets from point 1 to point 9, okay, source to destination. Each of the links in the network, let's say, is modeled by some stochastic time-varying link with some capacity that keeps changing over time. On any given day, you choose a particular route to send packets over. Okay, and on that given day, the link assumes some capacities, okay, given by these green numbers. And what you get to see at the end of the day is basically how much flow you got along that path. Okay, so in this case, it would be basically the bottleneck, the minimum capacity along that route. Okay, so minimum of all these numbers is, let's say, 1. You treat that as a reward for the day. You do this again for the next day, right? Select a different path, explore a different path, and you get some other reward, and so on and so forth. Keep doing this over time. Right? So the actions here are basically corresponding to selecting paths in your network. And this can be a huge space of decisions. It's an exponentially large space. Right? In the underlying variables, which are really the sort of unknowns around the edges of the graph, which is much more. And the goal is really to sort of learn online the route to the highest, let's say, expected bottleneck capacity. Okay? Notice that the feedback here that you're getting after each day is a very complicated function of all these numbers. So it's a minimum function, it's not linear, right? It's not linear, and so on. The point is, how do you come up with a principled framework for solve such problems? Okay, this is just an example of a very general class of math problem. But you realize at once that sort of the constant sampling algorithmic prescription is at once very general. Okay, so the moment you can represent uncertainty in your model, in this case the sort of the variables, the parameters that represent the edges of your routing network, you can immediately put a prior distribution on that. Okay, what you do at each time to make a decision is just sample the parameters from there, sample an entire model from your belief, try and play greedily the best action, in this case the best source to destination route. And then once you've taken an action, you get some feedback, statistical feedback, using which you can update your knowledge. Okay? So provided you can implement this rather simple sort of formula, you at once have an online learning algorithm. And this is fairly general. Okay? So one of the sort of things that we help show is that at this level of generality, you can show that the algorithm actually has fairly strong guarantees, as it should, because it's found to perform quite well in practice. Okay, sure. Okay, so that's sort of the punchline number one. And of course, it does perform well in experiments. So sort of the y-axis here represents the regret or sort of the degradation in performance by running one of two different algorithms. So the blue line is sort of the constant sampling version which knows this kind of structure in a structured problem with very, very many actions. The green one is sort of an algorithm that's sort of not aware of the structure and it's forced to sort of explore so much that its regret goes up. So this phenomenon is sort of observed very often. Right? So I'll talk about one more problem very briefly, which is sort of really an extreme version of the Bandit problem. You have actually infinite number of actions that you can potentially take. Okay, so think of, so this problem occurs in what is called function optimization with noisy samples. So the basic problem is you have an unknown function over some domain and you want to maximize this function with only noisy values. The only thing you can ask is, I want to play a point x and I get the value of f of x plus noise. Okay, and that is an unknown function. Okay, so this can be very general. Your domain can be sort of some multi-dimensional domain. So imagine that you're trying to train some deep learning system and you want to set parameters, right, to guarantee good generalization error. So you set some parameter, you do this whole thing for once, and then observe some value of the error, right? So the error in this case will stand for the unknown function f, and you're trying to optimize sort of a system by changing its parameters, right? So the domain is really a set of parameters in control, and in fact, there are no companies that are based on this idea called Bayesian optimization. Okay, they help you essentially try to optimize the system's parameters once you give them essentially a functional relationship. Okay, so this is one such company that sort of does this business using pretty much the tools that I'll show you now. So in fact, you can take this function sampling paradigm here to the extreme here. Since the uncertainty is on the target function, you can imagine trying to put a prior or a belief distribution on function spaces. Okay, so think of a nice class of functions over which there is uncertainty, which you want to maximize. You can put what is called a Gaussian process prior, which is sort of a nice prior on smooth functions. And at each time, you basically sample an entire function and play its optimizer. Okay, and that's what you do. It turns out that you can update your knowledge in the sense of prior very easily, which is what this Gaussian process paradigm allows you to do. And here, sort of, you're actually able to show pretty much the first guarantees for this kind of general function optimization problem in the non-parametric setting, because this is sort of an arbitrary function optimization problem, and also improve over the setting here. So this works rather well in practice over both synthetic experiments, which is the plot on the left, and actual sort of temperature sensor data that we ran this on the right. So essentially, the problem here was you have a room where you want to try and find the by trial and error the point with maximum temperature. Okay, and whenever you go to a point, you measure the temperature with some noise. Okay. So that's the punchline, second punchline, and thanks for your
So in all these problems, I guess my first question is, in all these problems, I knew the graph, but I didn't know the realizations of the capacities, right?
Yes.
Okay. So there could be another issue if I'm also learning the graph.
Yeah. So so that's a good question. If you have a model for the graph, you could perhaps extend the uncertainty to that level as well. Otherwise, there are other sort of ways of adapting in different ways to changing graphs.
Great, great. So, one more question while Ioannis is setting up, if we have one. Yes.
I mean, no, so the theory really works with reasonably general priors, but in order to implement this, it's much better if you have a conflict. Okay.
Great. Let's thank Aditya again.
This work?
Okay. Okay, so our next speaker is Ioannis Mitliagkas, who did his PhD here with Constantine and Chen. He also had the misfortune or fortune to work with me on a few projects. Then he did his postdoc at Stanford University, and he's currently an assistant professor at the University of Montreal. And have the floor.
Thank you for the invitation. It's super nice to be back here. The new building is kind of nicer than ENS, I would say. Okay, so let me get started. I will talk about deep learning, but in particular I will talk about how studying dynamics, which is the thing I like to do, of the optimization methods we use to do deep learning, how this understanding can help us scale them more efficiently, and also tune them to make them more accurate and faster. Okay? This right? Turns out I need one more step for my clicker to work. Okay. So deep learning has produced some very successful systems in natural language processing, in speech recognition, computer vision, across the board on complex tasks like those. Deep learning systems provide the state of the art. The asterisk here is that you do not always need deep learning to achieve state of the art results across on other tasks, okay? But complex tasks like computer vision, for example, you will be very hard pressed to find any good method for, let's say, for classification that does not use deep learning these days, okay? So there's a mystery behind deep learning. There are very complex models. They're typically neural networks are composed of many layers stacked one after another. There are a few groups in the world that know how to make them work. Taking the right steps to train them, to design them, to correct and debug them seems to require a lot of experience. And it's fair to say that it's generally not a very accessible technology to everyone, other than big companies in Silicon Valley and very specific academic groups. Okay? So this is the biggest cost, in my opinion, of modern machine learning. Hyperparameter tuning. What is a hyperparameter? It's, for example, the learning rate. It's this number that tells me how big of a step I should be taking when I'm doing iterative optimization. So to optimize my model, to find the right model to classify, for example, cats. Cats are important, you'll see them in the next talk as well. I start from some model that performs poorly, and I evaluate some objective function, and I look at this gradient, and it's telling me you should go this way so that you do a better job, okay? Whether I'm taking a small step or a bigger step, this is called the learning rate, it's a hyperparameter, and it's very important for me to get it right if I want to train a good deep learning model, okay? And of course, this effort There are a number of other hyperparameters, so it's not just this one. We will see one more called momentum, which is very important. But then there's hundreds of other, I guess, features of an architecture that we could call hyperparameters. And finding the right configuration can be a very daunting task. The effort put in hyperparameter tuning is often not reported, and you will read papers that read as if they were magic. So they will show you a nice picture of the architecture, and they will show you the results. Sometimes they will report the final configuration they found, but typically you don't realize how many grad student months went into this project, like finding the right magical configuration. So hyperparameter tuning. The other practical consideration here is deep learning typically involves very large models that require a lot of data to train. So the first point is if we don't have that much data, then we shouldn't be doing deep learning. So that's one takeaway. But importantly, even if we have the data, then that implies a lot of computation. Going through very large data sets again and again over many iterations until we get something good can take even weeks on modern hardware, okay? Sometimes a few months. So there's a lot of pressure and a lot of need to parallelize this kind of computation. What if instead of using one GPU or one modern, let's say, a powerful server, I used 10, 100, or 1,000? Can we do much faster? Can we scale, let's say, linearly by slicing the wall clock time needed to get my final model by 10, 100, or 1,000? And in this area of research, different academic groups and different companies have produced different methods and different frameworks for parallel optimization. I will discuss two main flavors called synchronous parallel and asynchronous parallel systems, and try to make sense of the second class, which has been traditionally a little bit more mysterious. Okay, but the theme here is we study those two topics, hyperparameter tuning and how it connects to parallelization, all through trying to understand the dynamics of momentum. So let me give you one slide of preliminaries. What is momentum, okay? So I told you, in order to get my model, to train my deep learning architecture, I need to minimize a certain function. So this function f here is what we call a loss function, and it's telling me how bad of a job I'm doing. In particular, if I'm very bad at classifying cats, this value of f at my current model w will be high. So I want this value to be low, right? In this case, I want to be down here. These are sub-level sets, let's say, and I want to be down here in this valley, which basically tells me I'm good at classifying cats. Okay, so the typical gradient descent method has me starting at some point up here and looking at the steepest way to go down in plain English, and just taking a step in that direction. And then looking again which way is downhill, taking a step in that direction, and so on and so forth. Okay, so this way I start from my current model. This is maybe hundreds of thousands or millions of numbers describing my current model, my current classifier for cats. And basically, I will update it by adding the negative gradient. That's the math. And that's basically all of the math you're going to see. So this is gradient descent. Okay? And we call it stochastic gradient descent because sometimes we do not use all of our training sets to evaluate this gradient, but we use small mini batches. We use a few images at a time, let's say 100, 200, something like that. So we get noisy gradients. Okay? That's what makes it stochastic. Now let's see what momentum is. It was introduced in the 60s I don't have the citation here. It just adds another term here. What does this say? It says that my latest step, like if I say WT plus 1 minus WT, is the gradient term I had before plus the previous step I took in the process of this optimization, right? And it has been observed and proven for a certain class of models, or a certain class of objectives. In theory, that it can speed up my convergence. I can get to this optimal point or close to it much faster. Okay, so it's very interesting. We want to understand it. It's very popular. It's used everywhere. So the first thing I'm going to talk about is how momentum connects to the dynamics of asynchronous parallel systems. I will describe quickly a theoretical connection. And then I will talk a little bit about how we use those lessons from that simple theory and the prototype we had to scale essentially deep learning for scientific applications along with Intel and Lawrence Berkeley labs. And if I have time, and I suspect I will not, I will tell you some couple of things about the recent project about adaptive tuning, okay? That's probably not going to happen, okay. All right, so how do we parallelize computation, okay? This is a typical architecture of how we can compute those gradients. I showed you earlier the gradients, the steps I'm taking. How can I parallelize all of the calculations needed there, okay? And this is one way to do it. It's a standard way. It's called synchronous parallel computation. And I have a parameter server which holds my vector W, the current model. And I have a number of workers here that take a mini batch of images, let's say 100, 200 images. They split them into smaller chunks, and they compute little noisy gradients each. These inverted triangles here are the little gradients, right, which tell me which way I should go next. In this scheme, there's a synchronization barrier, which means workers that are done early need to wait for any stragglers. Okay, and when they're done, we average all the noisy gradients. We get one gradient. We send it to the parameter server, and it gives us the new version of the model, and things start over. Okay, this is good because it's equivalent to sequential optimization. However, it can be bad if I have to wait a long time for any stragglers. Okay? On the other end of the spectrum, we have asynchronous parallel optimization, where now my workers work on their own mini batches. They each take 100 or 200 samples, and they take their time to compute their gradient and do not coordinate. There's no synchronization barrier here. This is faster. There's no straggler effect here. There's no waiting. However, there's something statistical happening here, which is described here. Let me try to explain it quickly. So let's study one iteration in the life of worker one, okay? At time t, my worker will read the current state of the model, WT, and take some time to compute the gradient, right? So this takes non-negligible time to do. So in the meantime, because this is an asynchronous system, other workers are coming back and they're writing their updates. They're sending their gradients back to the parameter server, and the model changes. WT plus 1, WT plus 2, all the way to WT plus tau, okay? At which point, presumably, my worker is ready to send back their gradient, right? But now, you see that this gradient has been computed based on an old version of the model, WT, and it's applied back on top of WT plus tau. This is what's called staleness, and there's a very simple way to model it as a random variable, okay? And without going into the details, basically, staleness acts kind of as fuzzy memory. My gradient here will be evaluated based on a random old version of the model. Okay? No, time is just ordered based on the on the parameter server's count. Okay, the parameter server just increments the timer when. Okay. So what does this mean? What does this imply for us? Why do we care about this? This resembles momentum. The fact that we're using some kind of old model, this kind of fuzzy memory, to compute our gradients, it resembles momentum, because momentum is also a kind of memory. I'm using old steps and I'm bringing them back into the current update. Okay, so I will not show you the math, but by using some great stuff I learned at analysis and design of networks, I don't know if Gustavo is here, we showed the following thing, basically. Okay, let's say I have my favorite network that I'm training, and I have one worker here, just sequential execution, and I manually tune my hyperparameters. And I find that 0.9, for example, is the optimal value for momentum. That means I get to some target loss, or to the optimum, in the least number of steps. That's what the optimal amount of momentum is here. Okay? And say I want to scale out, right? Add more workers. Basically, I tried 2 workers, I tried 4 workers, 8, 16. And I use the same algorithmic momentum. I tune my momentum parameter to be 0.9. What our theorem says is that I will get extra momentum on top of what I add algorithmically, and this is due to asynchrony. So the asynchronous dynamics act as if I had added more momentum algorithmically. All right, and this has an implication. This has a serious implication on how I should be tuning these systems as I'm scaling out. Okay, the details are not very important, but we worked on a simple system prototype to try to understand these behaviors, and we saw them in practice, and we studied a certain trade-off. As I'm increasing the number of asynchronous workers, I spent less time per step of my algorithm, per iteration, because I'm using more computation. However, I need more steps to reach to the same solution, to get the same model in the end. And it's because of this staleness I described. Okay? And to deal with this and to study this more carefully and to be able to fine-tune this trade-off, we designed an architecture that is a hybrid between synchronous and asynchronous training. Basically, I will take a fixed number of workers, organize them into what are called compute groups. Okay? Within the group, they will be working synchronously. Across groups, they will communicate asynchronously via a parameter server. And doing a large study on a number of networks, we were able to see, this is the important thing, this is wall clock time here, that the optimal configuration in terms of the number of compute groups is never fully synchronous. It's rarely fully asynchronous. It's typically some hybrid configuration. Okay? So if I have 1 more minute, I will discuss how we applied the lessons we learned doing this study on a smaller scale, up to 32 workers. We started a collaboration with Intel and Lawrence Berkeley Labs. They have a big computational cluster there. It's called NERSC. And we applied those ideas to do essentially deep learning on scientific applications at 15 petaflops. And they have a brand new cluster of almost 10,000 machines. And I will skip most of this, but the motivation here is that in certain scientific applications where you have a lot of data, it makes sense to use deep learning. However, it takes a lot of time to train, it takes a lot of time to tune, so its rapid development is out of the question. If it takes you 3 months or 6 months per cycle, that's not very helpful. So it's important to be able to scale and to tune those systems. And what we had here as applications was the high energy physics application, where we had almost a little bit more than 7 terabytes of data. A climate science application where we had 15 terabytes of simulated climate data, where the point was to do extreme weather pattern prediction and localization. And long story short, some of the lessons we learned was that, yes, using a hybrid architecture, we can improve things in terms of weak scaling. What is weak scaling? I scale the number of machines, but at the same time I also scale the amount of work I'm doing. The short description. What's more important is strong scaling, and getting to good strong scaling is a very hard task. So we saw that hybrid architectures were especially good at improving strong scaling, where we saw that synchronous architectures actually slowed down, going from 512 to 1,000 machines. And this is work that we're presenting next week at SC17, Supercomputing 17. And this was our hero run. Our biggest run was at 6 a.m. one morning. We had 20 minutes to use the whole cluster. Of course, we did not train any model to some reasonable extent, because we only had 20 minutes to set things up. But it's what they call hero run in the HPC world. And the goal there is the petaflops, okay? That's one of the results we're reporting. Our code has been included in the latest version of Café, as maintained by Intel. And this was our big pain. At that scale, tuning was impossible, which motivated our next project, but I will not be able to talk about this. Please come ask me questions. I'm sorry for running over so much.
So maybe we'll take one quick question while our next speaker is setting up. So any questions for Ioannis? So I have a question, Ioannis. So you were running, I guess you also have to mic him up.
Oh yeah. I will take care of that, yes.
So you were running computer vision. Was it the computer vision problem?
For this last big problem.
Yeah.
You can say that. You can say that they're both kind of computer vision problems. For high energy physics, we have those collisions of the in let's say in an accelerator. They collide those particles and they get measurements from different angles. So these are kind of like images from many angles, but they're not always the visible spectrum.
Okay, good. All right, let's start the last talk. Very good. So our last speaker for today is Dimitris Papailiopoulos, who did his PhD with me here in UT, and then he did a postdoc at UC Berkeley. And he's currently an assistant professor in the University of Wisconsin at Madison. So you have the floor.
All right, awesome. So first of all, it's a great honor to be back here and present in front of you guys. And this is, as everyone said, a very beautiful building. I will talk a little bit about some of my research work. I am working in distributed machine learning. And distributed machine learning is extremely slow, and I will explain today why this is the case. And I will also touch upon some of the methods that we've developed to speed up large-scale machine learning. And if you were waiting for cats and dogs, here they are. So the typical example of supervised machine learning is you want to train a classifier from a data set of, let's say, annotated examples of cats and dogs. You would like to train this classifier so that not only performs well with respect to accuracy on the training data set, but the hope is that it will perform well with respect to predicting whether it's an image of a cat or an image of a dog on the unseen universe of all images of cats and dogs. And the surprising thing is that this is possible right now. So we can build complex models that are operating at sort of state-of-the-art accuracy, and they can predict really well between different kinds of images. Now, the way that we do this algorithmically, so we have a very, this is somehow a simplified version of the algorithmic pipeline of machine learning. You start with your input data, and there is some preprocessing and some data cleaning that is happening. And then there's the black box of training, where Ioannis talked a little bit about it. Training basically takes the input data and essentially trains a model with the hope that once you're done training, once you've seen the dataset many times, you will output a model that will perform well on the unseen universe of images of cats and dogs. So the hope is if you give the model a new non-annotated or unlabeled image of a cat, it will correctly identify that this is indeed an image of a cat. And the interesting thing is that somehow the major computational bottleneck in this very simplified pipeline is essentially the training part. So this training black box is what's taking most of the computational research. And the reason for that is the following. So let's say we're in a simple setting, just have one CPU, and you just want to train a simple linear classifier. And you have a very simple data set, images of cats and dogs, and you have these two features, the size of the ears and the size of the snout. And you want to train a linear sort of classifier that can tell you, is this a cat or is this a dog? And the way that the prototypical stochastic gradient algorithm works, as again Ioannis mentioned, is the CPU will see an image of a cat, and then lights will be blinking, and it's going to try to figure out whether the current classifier is actually doing a good job with respect to that particular image. And then it will adapt the classifier that you have, and hopefully that will go to sort of a better point in the hyperparameter space. And this process will happen again, so you go to the next data point, and then lights are going to be coming on and off in the CPU, and you repeat this game again and again until you're somehow happy with the model that you have at hand. And this process will be repeated, so there are going to be many passes over the data. When we say pass over the data, it means sort of a full scan, like seeing each data point at least once. And somehow the challenge of this algorithm is the fact that learning is inherently serial in the following sense. Much like reading a book, you have to go through the examples one by one, and you might read examples out of order, but you can't read 2 pages at the same time. And that would be okay if that was a small book or a small data set, but the point is that in practice, for example, when Google is training really large neural networks, training complex models on really large data sets can take up to weeks. And that is way too much because that slows down our somehow cycle of interacting with data and doing hyperparameter tuning and so on and so forth. So what do we do now? And the simple thing that we might say is again similar to what Ioannis was talking about. Train at scale, go on Amazon C2. You can get your favorite instances, CPUs, GPUs, your favorite amount of RAM, combine them in the way you like it, and run it as much as you like. And hopefully that will work well. And somehow the prototypical algorithm paradigm is to distribute the computational effort across the machines that you emptied. So let's say now you don't have one machine, you have, let's say, X number of machines, and now you have many learners, and the point here is that they will go through a smaller number of examples, each individual sort of worker. And somehow the hope of this algorithm paradigm is that at the end of the day, if you have X machines and you parallelize the computational effort across them, this algorithm will be X times faster than the serial algorithm. So, yeah, that's it. So, it's closed. But I hope it was as easy as that, but it's not really true. So, I want to talk a little bit about this paper that came up in 2012. This is one of my favorite papers in distributed machine learning. 2012 is ancient times on the machine learning research timeline, but it's still very relevant. So what they did in this paper, this was by what's now called Google Brain. They built a distributed system called DistriLeaf, and they did training on a number of machines using a distributed variant of stochastic gradient descent. And they had at some point this figure. So what this figure shows here is on the x-axis, you have the number of machines you deploy your algorithm on. And on the y-axis, you have training speed up with respect to some particular accuracy. So the different lines here basically correspond to different models, but you can just focus on simply the red line. And observe that, for example, on 16 workers, you get 16 speed up, but things start to change as you start scaling out more machines. And I want to ask you, what is wrong with this curve? So what's happened here that we don't like? So what is wrong with this curve? Exactly right. Exactly right. And as a matter of fact, if you were to plot the optimal speedups, it would be 10 stories up. So let me zoom out a little bit. So that's where the optimal is. So that's pretty depressing, in a good way, because there's research to be done. So the reality is far away from the realizable thing. You get 1 to 2 order of magnitude slower algorithms, and the question is, why is this happening? And I just want to note that this is not something that we fixed. So we still face this problem. It's 5 years after this paper, and we still don't know how to fix this. But at least I want to start by understanding what is causing this bottleneck. Why do we have this speed of saturation? And there's a lot of, it's a complex problem, and there's a lot of sources, but one of the key sources of this speed of saturation has to do with communication. So the simple distributed algorithm we're using is following a master-worker paradigm. So in this setup, you have a master who is doing distributed computation, that's storing the model, and it is outsourcing the gradient computation to a bunch of worker nodes. And somehow, once these worker nodes are computing the gradients at the global model, again, this is the same algorithm that Ioannis was talking about, what will happen is they will seep their updates back to the master. So somehow a very important parameter you can tune is what I will call for the stock the communication knob. So what you will do is basically you will tune how often they communicate updates back from the master, from the worker to the master, and then the model from the master node to the workers. And there's some very interesting observations to be made here. So this is a very simple experiment. I'm plotting now the speed up, not to reach the particular accuracy, but to do a full scan over the data set and compute one gradient per data point. And the y-axis is the speed up for a single pass over the data, and the x-axis is how many workers am I using in this implementation. So this is for a sort of simple neural network on CIFAR10. And what I've changed here, so the different curves, are basically the frequency of communication. For example, the blue curve, I'm communicating from the workers to the master after 64 updates. And the red one is after 4,000 gradient updates. That's how often I communicate things back to the master. And the interesting thing, the most significant thing to observe here is that the more infrequent the communication is, the better the speed-ups you get with respect to how fast you scan through the data. So somehow from a systems perspective, smaller communication, once you turn this communication knob as small as possible, implies better speed-ups. But the issue now is that unlike, if this was a matrix multiplication, things would be fine, but somehow the thing that you're optimizing has a statistical accuracy. So you're aiming for some particular training accuracy. And if you start looking at that, then the picture sort of changes. So now what I will plot is the number of scans or passes over the data I need as a function of the frequency of communication. So on the x-axis, it's after how many updates do I let the workers communicate back to the master. So again, this is sort of the period of communication. And on the y-axis, I basically see how many passes do I need over the data to reach 95% classification accuracy on the particular task I have at hand. And the main observation to be made here is that essentially, the smaller the communication, the worse the prediction accuracy. So somehow, if you communicate a lot between master and worker, that leads to better models. You don't need too many passes over the data to reach the same accuracy. And when we did this experiment, my initial question is, why is this happening? Maybe we're not tuning the algorithms right. Maybe the problem is too particular. And essentially, what we see is that there actually does exist there's two forces. So the systems perspective tells you don't communicate. The statistical accuracy perspective tells you communicate as much as you can. And this is also quantifiable. So we have a theoretical paper. I will not talk about the theory. But the point of that paper is to say that every problem, convex or non-convex, for example, training a favorable neural network, there is sort of a frequency of communication that if you go below it, if you don't communicate too often, this will be translated in a penalty in the accuracy of the algorithm. So this was not sort of a bug of that particular problem that I showed you. This is actually quite fundamental. And the issue now here is somehow we are bound by this fundamental issue of communication, that no matter what you have to do, you have to communicate at a particular rate between masters and workers. So there's several things you can do. Maybe you can have a faster network. If the network was at the speed of light, you would not have this issue. But I'm not a network kind of guy, so I don't know how to fix this. But two other things that you can do is maybe change the model, change the neural network that you're optimizing, or use a different algorithm. So starting with the first, one interesting thing, so this is ongoing work with some collaborators from UW Madison. We basically saw the following. So let's say that you have your favorite neural network, and you start playing sort of an accordion game. You're allowed to have the same number, you have the same number of parameters, but you can shrink the network and make it wider. And you can also stretch it and make it really deep, but kind of skinny. So what we're able to show basically is that in terms of the frequency of communication or the amenability to distributed speedups, wide networks are better than deep. So somehow something that has not been really studied in the literature of machine learning is the fact that you don't just care about the statistical accuracy of your models, but you also want them to be amenable to distributed speedups during training. Now, moving on to a better algorithm, again, you have this setup of master and worker and this communication that is happening between these nodes. So instead of using somehow the vanilla version of stochastic gradient, which is well tuned for a single machine, you can start asking, well, if that costs me a lot to communicate, maybe I can use a lower precision or a compressed version of the stochastic gradient descent algorithm. And this is something that people have been looking at recently, the past couple of years. But one issue with somehow traditional quantization is the fact that you can do limited compression, so you can go between 32 bits down to 2 bits, so that's sort of the maximum compression you can expect. And the other issue is that somehow this element-wise traditional quantization is somehow oblivious to the geometric structure of the problem that you're solving. And what we basically realize is the following. So when you look at these little gradients that the workers are sending back to the master, you can sort of think of them in the following way. So you have your neural network, and somehow that gradient that you're sending back, you can view as a matrix that is cut into slices, and each slice basically corresponds to a different layer. So each slice in this gradient matrix is basically the gradient for a particular layer. And it has some interesting local geometry that the element-wise quantization that people are using in practice is not really preserving that geometry. So again, this is joint work with collaborators from UW Madison, and the first experiment that we've done is basically, well, let's look at the spectral profile of these matrices. So they have some interesting geometry that we can take advantage of. And what we see is that if you look at these little filters, they are not random numbers. They actually look like having some kind of a structure. And we did the eigenvalue decomposition, and we basically found that in the spectral domain, the power of these matrices is contained around very few elements. So that somehow the natural thing to do now is, okay, maybe instead of sending the full matrix, do a quick lower rank decomposition and send a few spectral components of that. And that somehow would be quantization in the spectral domain. And the interesting thing is that this simple idea is able to give us a 4x faster algorithm compared to running vanilla stochastic gradient. And we're still running experiments on that. But I guess my point with this, and I will start concluding, is the fact that traditional algorithms for machine learning have been well tuned to the single machine case. But now once you start deploying things in a distributed setup, there's many trade-offs that arise. There's communication trade-offs, and this forces us, or makes us start thinking about having models that are actually tuned for these distributed setups, but also going beyond the traditional stochastic gradient algorithm. And I just want to note that, again, the 2012 paper is still relevant. So this is speed up curves for a single learning task on TensorFlow right now. Again, there's a huge gap still between realizable speedups and optimal speedups. And I think this is a very rich area of research, and there's a lot of impact to be made still. And I just want to talk very briefly about open problems. So the first one that you might think of is, why stick kind of a master-worker setup? Maybe you can have a more decentralized peer-to-peer setup where workers talk to each other and maybe have more masters than one, and maybe this will allow you to have faster speedups. I don't know the answer, we're still looking into these things. The other thing that I feel is a very conceptually interesting and important problem is figuring out what is the optimal quantization and compression of these algorithms, both during training and during inference on the model itself. And somehow we have a lot of background on quantizing things in a good way, but these problems have some specific structure. And the question is whether we can exploit this structure to have better solutions and have smaller models that, hopefully at some point will, we'll be able to efficiently shrink and fit them in edge devices. And the last thing that I think is very interesting is what people call federated optimization. So you have a bunch of GPUs, you have a bunch of CPUs, maybe a few edge devices. I would like to do training on all of those, although it's sort of an inhomogeneous kind of system. Again, we have not solved the single master worker problem yet. Federated optimization is even harder. We still have no good ideas of what is a good algorithm for this era. And another interesting thing that arises there is the issue of security. You can have a lot of machines in your system training at the same time, but maybe you have some adversarial nodes or you have some adversarial attacks. The question is how can we somehow robustify these algorithms against worst case setups with respect to adversaries. And the goal of my research is concluding with that, to try to make machine learning, distributed machine learning faster, make it more robust and secure. And somehow the note that I have to all of you, but particularly to graduate students, is that somehow, back in the day, you would have an impact on machine learning or optimization if you just knew some optimization and maybe some information theory. But I think now the very important component that needs to be taken into account is the aspects of the system itself and the architecture of the system that you're running these algorithms on. And I'm working in the middle, and that's where magic happens if you want to be there. And I will conclude with that.
So I guess we are only 5 minutes or 8 minutes over. Is there maybe one question for Dimitris? Or no, there's no. Okay. So there's no questions for Dimitris. We'll take it offline. I just want to say that it's really great to see our students, go in top universities and do amazing research. So I'm personally very proud of all the work I saw today. So let's thank all the speakers. Catch them in the coffee break if you have more questions.